Hello, and welcome to the latest episode of Ask a Nerd, the show that takes you into the heart of the electric vehicle industry and where we talk about the technologies that go into zero emissions vehicles. Today, we're going to be talking about batteries and how they enable range, one of the most significant topics that people will discuss when you're talking about adoption of electric vehicles. One of the most significant products to hit the market recently, the Ford F-150, carrying around a 125 kilowatt hour battery pack to meet its range targets for a large vehicle. This battery is approximately 5 times the size of the first Nissan Leaf that was on the market. Is this a trend that we're going to see continuing? Today, we're going to talk with our nerd about whether there's another way. I'm Tom Brimble from Green Plates, and here's Cecile Perra to introduce our guest.
Hi, everyone. So, I don't know you, but trying to understand fast charging for very small battery is quite confusing. For example, if I take the family of Volkswagen that use the same platform, the MEB, they are all using the same battery pack design. And this pack can be small or larger just by removing some of the module. So you expect that the same battery pack would get the same property to fast charge. And you expect the timing to recharge depend on the size of the battery and the charger you have. So if I use the same charger to recharge a big battery or a small battery, then I would expect not to have delay so much. But when I see what are the value, if I have a smaller battery, I don't save time to recharge. And it seems to be confusing for me. That's why I think it's better to ask a nerd why we have some problem about fast charging for small batteries. So before we introduce our guest of today, I'm going to explain you how it works. So we are here for about 40 minutes. We are going to get some educational content and review what exists on the market in terms of fast charging for small batteries. We will talk about battery pack design, again for small batteries. We will have a case study, sorry, there is a misspelling here, on the Volkswagen ID.3. We will, of course, talk about the 800 volt because it is one of the key technology for fast charging. And we will review some EV trend. Meanwhile, we will have some question and Tom will come at the end to ask this question to our guest. So today we welcome our guest, David White from Deneka. Hi, David. Can you present yourself?
Great. Thanks for the invitation. I've enjoyed your first few episodes. I hope this one's as interesting. I've been working on lithium-ion batteries since about 2007. First of all, at Jaguar Land Rover, where I ran their HEV and PHEV battery projects. And then for the last 4 years, I've been at Deneka. We were founded about 4 years ago. Our vision's about a world where the environment isn't sacrificed for energy security. What we do to try and make that happen is removing barriers and inspiring change towards adoption of sustainable energy solutions, mostly to do with batteries. So my team, with system engineers, electronics, software, and test engineers, we're working to design the right product for our customers. Making sure it's a safe product with efficiency on cost and weight and size, and also that we're making a product that can be scaled to work on the sustainability topics that are so important at the moment.
Can you just say how you end up to work on electric vehicle? What is your story?
Sure. I trained at university as a mechanical engineer. Did quite a lot of MATLAB simulations. That was something that I did a lot of during my degree course, and then I got a job working in a research department between a university and Jaguar Land Rover, working on simulating lead-acid batteries for starter motors, and then from that worked through research into lithium-ion batteries, and then became one of their first battery engineers working on high voltage systems.
So you're in batteries for a long time. So to start, we can see obviously that EV are trendy since last 10 years, I would say. And obviously we have seen a bunch of different technologies, different cars. trends are very clear. We can see that the battery pack are increasing, range that are able to do the cars are massively increasing. We are now nearly 1,000 kilometers of range for some of the latest developments. We have also fast charging because we can charge now up to nearly 300 kilowatt DC. So that have been the major trend over the last few couple of years. But when we see this is quite concerning because we see that the size of the battery pack are dramatically increasing. Can you comment about this? What sort of problem it creates and how the business should think about that?
Sure. Tom mentioned the launch of the Ford F-150. At the launch event of that, one of the journalists asked Jim Farley, CEO, what keeps him up at night, and he said batteries and the materials that go in them. And so I think the lithium demand versus supply is clearly something that's on the agenda for a lot of people. Tesla were even suggesting that they were going to get into lithium mining in their Q1 earnings call because they see it as the biggest barrier, the biggest barrier to the Earth's transition to sustainable energy right now. So the demand for lithium is there, and the supply there's going to be a gap, and some people are predicting this all the way out to 2030.
Yeah, it of course changed a lot of things for the business margin and things like that. We also see that in terms of infrastructure to recharge all of these cars start also to be a problem. So home chargers are quite okay, I would say, but there is a lack of fast charger anyway. Do you believe we can cope with this problem?
Yeah, so with EV sales really taking off, particularly this last year, I think it was a doubling on the previous year, something like 5 million in 2021, 2 and a bit million in 2020, up from probably only just over 1 million in 2018. So yeah, there's far more electric vehicles on the road. These graphs are for the US. It's Type 2 charging versus DC fast charging. So yeah, I mean, both of those curves are definitely going in the right direction, nice and steep. But yeah, DC charging's got a bit of catch up to do.
So preparing this episode, you made this very nice graph where we can see a lot of information all at the same time. So we have things about the range, we have things about the charging time in terms of mileage you can put in terms of minute of charging. And also some of the battery size, we can also see one of the main trends. Can you comment a little bit what you see on the market for the moment and where we are?
Yeah, so we're comparing the single charge range, so what you can get out of the vehicle from a fully charged battery to depleted, and then on the y-axis looking at how fast they can recharge. And we've had that big focus on energy density and cost of the battery, and that's really been necessary over the last 10 years to get the products to be credible. I mean, to make EVs work for any user case, we needed that improvement in range and cost. We're now at a point where to actually think about what makes a flexible vehicle and what truly does the customer want from a vehicle, and sort of re-look at some of those metrics and see where does the industry need to go next. So in terms of cost, at the moment, if we trend more and more towards larger and larger batteries, the cost of those batteries, we've got down to a certain point. There's discussion now about does that carry on trending down, but then against these raw material issues, like really where that cost is going to go. In the last year, we've actually had cost increases of maybe 10 to 20% from quite a lot of cell manufacturers. So it's certainly right now those costs aren't carrying on trending down. So cost efficiency. To really do cost efficiency, actually, can we get a smaller battery and can we make better use of it within the vehicle? And the key to unlocking that is to be able to recharge quickly. If we can get to the point where we can recharge a decent number of miles within the time that you have a normal sort of rest break at a service station, then we're truly making a vehicle that's as flexible as the internal combustion engines that they're going up against.
So let's talk about this battery pack design with this objective to get better fast charger. So we can work on different level. We can work on a cell level, the chemistry, the module and the pack, the whole vehicle, the system level, I would say. So let's go through all of this. This is one of the most interesting things I have seen when we prepare this presentation. I was not aware about that. Can you explain what we can see here and what we can conclude, and why is that important for fast charging?
Sure. So we're looking at energy density against power density, and each line on this graph is a different cell type. These are all commercially available, mostly cylindrical cells, though pouch and prismatic cells, it doesn't make a huge difference where they fall on this plot. So for each of the cells, we can see as they move to the lower right hand half, these are high energy cells. They're cost optimized cells, because that's what we've asked the cell suppliers to produce. We've said we want more kilowatts, we want more kilowatt hours per liter, and we want the cost out of them. So they've created those cells, but what we've lost the power capability from them.
So you mean there is a trade-off between the capacity, so which is related to the mileage, and the power in terms of also charging, which can give you better option for fast charging. So it's
Absolutely.
difficult to get both of them. So either you need to choose capacity and range, either you need to get power and charging. Is that correct?
Absolutely, and these higher power cells, these sort of more performance oriented cells, they do already exist. They're in use for motorsport EVs, so Extreme E, Formula E. They're in use for those kind of things. Obviously, the volumes aren't there, so at the moment those cells are more expensive. But there's no real reason that they need to be. They've got a little bit more aluminium and copper in them, but for the same amount of energy, they've got the same lithium content to them. So those raw materials don't particularly change a huge amount. So it's a volume issue of if those cells were being sold in more volumes, the cost would come down. They've also just not had the amount of research put into them, because it's not where the big volume industry has been going. It's not what we need for consumer electronics, and it's not what we've been telling the cell suppliers we want for our large volume EVs. So even with today's technology, you don't have to take too dramatic a decrease in energy density to get a significant improvement in power performance, which then translate into your recharge times.
I think it's worth mentioning for the public that it is also related to the C rate, because people hear about that C rate. So it means that if you can charge and discharge fast, usually you get a high C rate, and most of the normal BV we have are low C rate.
Yeah, absolutely. And so typically those ones down in the BEV area, they're cells that are typically 1 to 2 C rate, whereas the motorsport BEV we're looking much more sort of 10 C rate. But there are cells out there commercially available now that will do 30 to 50 C rate. They're very niche application cells, and they're even more expensive than what we're considering in this presentation. But the range of what you can make a lithium ion cell do is huge.
So usually when you think about high C rate and things you want to fast charge, you tend to believe that it is highly related to the cooling of the battery. And we see that depending on the car manufacturer, there are of course a lot of different options, immersion cooling, cooling plate, whatever. But even if we take the best that are available today, some get charged on the side, some decide to cool on the bottom of the plate. Do you believe this has an impact, and how that can change something for fast charging or range or whatever?
Sure. So I mean, one of the benefits of choosing the right cell for your application is these higher performance cells actually have a lower internal resistance. So that gives you an immediate benefit in the heat generation of them. Some of the technologies, so choosing between side cooling of a cell or cooling on a plate on the base of a cylindrical cell, there's not a huge difference from the battery perspective. Side cooling, you might have a slightly larger surface area, but then you've got a slightly longer heat path from the jelly roll, the chemistry inside the cell, out to the cooling system. It can be a bit harder to assemble. The tolerances are a bit trickier, but at a large scale, those are things that you can deal with. But the big thing really is that you've got to always think of these things in the bigger picture. That's what the systems engineers really do. So thinking about it at a vehicle level, Lucid have put the cooling plate underneath the cells, and that's automatically increased the stack height of their battery pack, maybe by 8 millimeters or something like that, which on their vehicle, if the battery height translates into the actual total height of the vehicle, if reducing the battery height meant that they could bring the roofline down a little bit, they possibly could have had another 0.5% improvement in the drag area of that vehicle, which is something they already spent a lot of energy optimizing. So thinking about it in terms of that, maybe they didn't have the wheelbase to make. Obviously, the battery pack has to have a cooling system. So if you don't cool from the bottom, you've got to cool from the side, and so the battery gets a bit longer.
I think it is interesting for the public or for people listening what you say to realize that the cooling get also an impact on the aerodynamic of the car, which is not something I've thought about before we come up to make this slide. That's, I think, quite interesting. So you came up with a nice case study about the ID.3. So when I started this introduction, I explained that for me, it is surprising and disappointing that you cannot really charge better a smaller battery. What could we do about that if we take this example of the Volkswagen?
Yeah, I think it's a good case study because obviously we know that, you said this is the same platform, so we know that they've got the charging capability to put energy into these vehicles, and they've got this strategy of sort of depopulating parts of the battery, which is quite common. I mean, lots of companies do that. You keep the same sort of outer structure of the battery and then take parts out of it for your lower spec, lower cost.
Modularity, it's the word everyone wants.
Sure. So yeah, I thought we should look at redesigning it. And in terms of these three cars, we can see the single charge range there drops by, I don't know, what is it, 100 kilometers per vehicle. But equally the charge, the kilometers per minute. So the Pro S, I think, did about 45 kilometers in 5 minutes. The Pro was 35 and the Pure is just under 30. So it's the same efficiency vehicle. There's no reason that the smaller vehicles should have a lower ability to put that energy back in, except that the battery must be limiting it. So we can use this as a use case and say, well, what if we change the battery? So thinking of those, we've got a step from an energy cell to a performance cell, and then to a really high power cell.
That type of cells that exists. You are giving here an example of something that could be done, right?
Absolutely. These are off the shelf. I mean, these are cylindrical cells that I've taken the data sheets from because they're a bit more open source available, those data sheets, than some of the prismatic ones. But again, the numbers all come out pretty much the same. So yeah, if we took a 10% hit on the energy, if we take the base spec version, the Pure battery, and make it heavier so that we can get that energy back in, so we keep the same single charge range, but put a higher power cell in there, what does that do to the power that battery pack can accept and recharge? And then if we go for a really extreme case, with that size of battery bay that they've got underneath the ID.3, what's the highest power cell that we could put in, keep the same range, and what would that give us in kilometers for 5 minutes? And the purple line there, putting the performance cell in, gets us to 50 kilometers in 5 minutes, which is actually better than their current top spec vehicle. So, if we're at 50 kilometers in 5 minutes, you'd probably want to go a little bit more than that. Going to the really high spec cell, you could actually get a battery in there that would do 150 kilometers in 5 minutes. which is above the Lucid. A little caveat on that: you'd actually need a better charger than they've got on that vehicle to do that. You'd need a really top spec charger to put the energy in fast enough. But you can make a very compelling vehicle, which has a far fewer raw materials in there. It's still lighter, and probably you'd actually be able, from Volkswagen point of view, they could probably get a better margin on it if they were able to advertise that as a vehicle that actually has better performance. It's a lighter battery. It's got slightly less range, but you can fill that range up. You can pretty much entirely fill that range back up in 10 minutes.
But of course, at the same time, this makes the strategy of Volkswagen slightly different, because they use large volume and they want to get the money on the fact that they have larger volume. So obviously, they choose this strategy, their current one, because for them it's.
They can keep a decent chunk of that margin. It's got a €4,000 better margin on it. So, and then that's all of this is using costs at about I think it was about €160 per kilowatt hour.
So if we move on and now talk a little bit about 800 volts. So when we're preparing this talk together, we had a lot of discussion about this 800 volt technology and what it means for fast charging. So obviously, the power equal U times the current, so the voltage times the current. But if you can increase the voltage and reduce the current, you also can reduce the losses. That's the basic point. Everyone understands this. Where it comes tricky is we debate together where this limitation from charging is from. Because if you do not put any other constraint, getting U times E or E times U makes no difference. But if you put a constraint on what is available on the charging infrastructure in terms of the current that can it support, of course, when you double the voltage, you can, of course, increase really a lot the charging, nearly double it, of course, related to the loss. Can you explain and comment a little bit about that? Because it's a point I have discussed with many people, and there is no always a common understanding of what we mean here.
Sure, and like you said, it really depends where the bottleneck in the system is. If from a pure battery point of view, if you take the same number of cells, and so the same energy mass of cells, if you configure it into an 800 volt battery or a 400 volt battery, the performance is the same, and the recharge time theoretically is the same. The only real difference is where you've got the sort of the connectors out to the rest of the vehicle and the final pack bus bars. Obviously, they have to be bigger for the 400 volt battery because they've got to carry more current. But the sort of the top level battery specs stay the same. But if your bottleneck is the charging infrastructure and the rest of the vehicle, then clearly going to the higher voltage and reducing the current gives you much better performance. So, it really depends where the charging infrastructure providers go with this, and the trend definitely seems to be towards going to the 800 volts. It means that the cable between the charger and the vehicle doesn't have to be the size of a fire hose. So
actually, except Tesla, nearly everyone is now going to 800 volt, because Hyundai, the last platform, is 800 volt. Porsche, of course, is 800 volt. Not for that, even BYD in China is 800 volt. Lucid, I think, is even higher than this. I think it's 900 volt, but it's a major trend, right?
Yeah, absolutely. And Tesla control their charging infrastructure, so they're able to make sure that their vehicles and chargers match each other. So they've done that. The rest of the industry could do that. If the rest of the industry decided that 400 volts was the answer and was prepared to accept bigger conductor sizes for the charger, they could do the same as Tesla. There's not a big. Again, I'm only really talking from the battery's perspective. There's not a big cost difference really for the battery. Having an 800 volt battery is actually a bit more challenging. You've got to have more sensors. You've got to have more balancing circuits to keep all of the cells in balance. The savings off the bus bars and cables, they're not that dramatic. So it's quite a hard cost sell from a pure batteries perspective.
So we can talk about what it changed in terms of the battery pack design. So of course we are not going to give all the theory again, but we understand if we change the current, we can save the size of the cable and the bus bar. We of course get the infrastructure of parallel and series, but it changed also things. For example, on the BMS, we had a discussion with Umut on our first episode. And I understand, for example, going to 800 volt get a lot of consequences also for the electric motor or the inverter. Can you also comment a little bit about that?
So for the BMS, you need a bit more space on a lot of your PCBs because you've got higher clearance distances that you have to leave so that the voltage doesn't jump from a high voltage side to a low voltage side. So the safety gets a little bit more challenging, but most of that's just space. Some of the component costs go up a little bit, and you also need more of these components because whereas before you had to measure enough cells to get to 400 volts, you've now got to measure enough cell voltages to get to 800. So you've got twice as many voltage sensors. But yeah, you can save a bit on the cabling size. Hopefully you lay your battery out anyway so that you've minimized the number of bus bars, the number of pack level bus bars that you've got in the battery. So keeping them as short as possible is something you should be doing anyway. But yeah, I can't really speak to motor and inverter design, but clearly it has an impact on what they're doing. And yeah, having smaller section.
As a ballpark, someone told me that when you go from 400 to 800 volt on the inverter, you can save about 10% of the mass on the inverter. That's quite, I think, interesting.
Yeah.
So we can talk now a little bit about some of the EV trend, other of course than the 800 volt. So one of them is to get thermal management and preheating of the battery. So for example, I know that when the Porsche Taycan, you are searching for a fast charger in the screen. If the car knows that you are going to charge, it starts to preheat the battery in advance. So when you arrive to charge, you are already at the optimal temperature. Is that something used now quite a lot? Why we do that? Can you also explain? And I believe this is one of the major trends we need to discuss for fast charger if we want to better charge.
So over the long term, heat is not good for batteries. So over it increases how quickly they degrade. But over the short term, what it does is it significantly drops the resistance of the cells, which then means that you can use them at higher power and put the energy in quicker. So yeah, I think this integration between your sat-nav system where you've put your route in and you've told it where you're expecting to charge up, and the cooling system, the thermal management system, either just to stop cooling the battery as aggressively or possibly even to actively preheat the battery so that when you get to the charging station, you're in this low resistance state and you can make the most use of the charging station and then carry on. And then, of course, go back to your normal cooling system regime. So the length of time that the battery spends at hot temperatures to be ready to charge is minimized, and it has less impact on the battery life. I think it's becoming fairly common to do this. And yeah, it needs that integration between the people designing the battery and designing the user interface and the sat-nav system and obviously the rest of the infrastructure with all of these apps that have the charging locations on them. So yeah, I think it's a good trend.
Of course, on this graph, I didn't put very high temperature. I use a sun mild weather, British weather, I would say here. But if you become too hot, of course, it's also not good. So you have not to eat too much. I say that for people who may forget.
Yeah, and we're talking, typically you'll operate a battery maybe 20 to 30 degrees, like during normal driving. So if it gets above 30, you'll start cooling it quite aggressively. And then once you get down to 20, you'll really back that off because you start to lose performance if it goes too much colder. Batteries are great in that they do sort of generate a little bit of self heat to bring them up to those operating temperatures. During fast charging, I don't think you'd target much above 40 to 45 degrees. We're not talking really high temperatures.
So another key technology everyone talk about is, of course, the tabless from Tesla. Is there any importance of the format of the cell, and what does it mean for this aim we are trying to do to get faster charging for smaller battery?
Sure. I mean, between the different formats, so cylindrical cells, prismatic cells, and pouch cells, I think we can see just from looking at all of the different OEMs and what they're doing that there really isn't a consensus, and you can use each have their pros and cons, and by the time you're building a full pack, it's pretty much all evened out again. So some of them need more structure around them. And so there's not massive differences between them. The tabless cell, I mean, that's a great example where the engineering team has really come together with all of the different levels and stopped doing this subsystem optimization and are focused on how do we actually make the best product. Having that tabless electrode, it is heavier than having individual tabs. You know, there's continuous tab there where to have a pure energy cell, you could get rid of a lot of them and save a little bit of weight out. But what it's done there is it's given them a really good thermal path so they can get the heat out and to the base of the cell, or for Tesla mostly they seem to be sticking with cooling on the side of the cell. So you can get the heat out really nicely. And it also makes it ready to be used as a high power cell. They can take that design, and by changing what they're doing with the electrodes, they can tune the energy to power ratio of that cell, and they don't then get compromised by the mechanical, the geometrical design of the cell. So they can really tune that a lot better than some of the other cell designs.
I also understand that from a technical point of view, getting the tabless means that the lithium and electron do not have to travel all the way around. They can just go quicker because they can get
absolutely. That sort of the electrical path. It's essentially the same as the thermal path. The shorter you can make it, the better you can do. And you can do the same with prismatic cells. Pouch cells particularly. There are some incredibly high power pouch cells available where they do very similar things by having stacked layers and making the whole of the end of that layer a tab. So the image there you've got with the tabs at opposite end of the cells. So one of the thermal paths comes straight to one end and the other one goes straight to the other, and with a really big thick tab. So you can do the same kind of stuff with regardless of what shape battery you're making.
So one of the last trends we have is about wire bonding, which I believe is difficult for some people to understand. So we put an illustration here. Can you explain what we are seeing here and why is that important?
Yeah, so this is just with cylindrical cells. So again, thinking back to the sort of Tesla and Lucid designs, Lucid had a tech talk recently where they showed ribbon bonding. So they had ribbons of metal between the top of the cell and the bus bars, and we're talking about having different sizes of ribbons to really minimize the losses. Whereas Tesla, I think all of their designs so far, they just have one wire on each side.
So when you say the size, you mean the thickness of this?
The cross-sectional area, because obviously you've got all of the current of the battery going through these wires, and some designers are using these wires as mini fuses. So you have the one wire per cell, and you know what current it fuses at. So if you have a single cell fail or go short circuit or overheat, you can
I see.
that cell can be separated from the rest of the pack. But having that fuse in series the whole time, it's warm. It's got some resistance to it. So we did some testing a year back or so to really look at how we could optimize that, and found that if you do this asymmetric bonding, so you have one wire on one terminal and then multiple wires on the other, so you've still got that fusing performance if you need it. But on the other side, you've really minimized your resistance losses. We found we could take a huge amount of material out of the bus bar, because a lot of the time the bus bar is acting as the thermal inertia, and actually you need that bus bar to to absorb the heat and then radiate it off into the pack. You can actually get a lot of mass out of that bus bar if you reduce your losses between the cell and the bus bar by putting more wire bonds in.
So which car manufacturer are using this? You say Lucid is using this?
So most people with cylindrical cells are using wire bonding. Tesla vehicles are obviously the biggest volume of those. Lucid are using a slightly modified version with.
And it's something you can use only on cylindrical cell. You cannot use this technique for prismatic or pouch. I don't know. I'm asking.
It works really nicely for cylindrical cells because it doesn't penetrate through the cell can at all. It's not like laser welding where you need to sort of really put some heat into the system. It's a very low temperature thing, and cylindrical cells have very thin walls. Prismatic cells, you typically have a much thicker terminal, so you can use laser welding on them, which often and laser welding often suits itself to higher volume processes. We do both in our facility. We have options to work. We've got laser systems and wire bonding, so we can pick and choose by the project.
So I think it's time to get now Tom with us, and he may have some question for you. So I step back.
Thanks, Cecile, and thanks, David. A huge amount of detail to unpack there. It's a good job we're recording these sessions, I think, so that people can come back to them on YouTube and dig into those slides. Lots of detail. So we did have a number of questions submitted, and the first one is talking about, so faster charging, is there another way with regards to battery swapping? So I guess this is the alternative in terms of, high power charging. It's a quick event. We've seen companies being successful more recently, or more successful than Project Better Place was in China in managed to commercialize battery swapping. How do you see that comparing versus high power charging?
Yeah, I think that's really interesting. I think it depends. Obviously, both are technically feasible. We've seen that demonstrated, and I think particularly it seems to have taken off a bit more in China. I do like the concept of being able to do the battery swap and choosing a different battery each time. I know that some of these companies are saying you can, during the week, perhaps you choose a smaller battery, and then if you want to do a longer journey, when you go to the battery swap station, you choose a larger battery. Obviously, it's a lot of infrastructure. I don't really know the economics of it. But yeah, both from a technology point, both answer the same questions of how do we make the cars more flexible? How do we minimize the amount of raw material that we're just dragging around with us when we don't need it most of the time? I like them both.
Yeah, and I guess clearly there's the systems integration challenges of having a huge amount of the floor structure being removable as well. That we saw with, yeah. Right, that was from Martina. Sorry. So the second question is regarding durability. Okay, so this is interesting. So for the different C rates of cells, are the higher C ratings less durable than the lower C ratings? So I guess in terms of number of cycles over a life, would you see a shorter life for higher C ratings?
If you take the same cell and run it at a higher C rating, you get a durability drop. So you'll see those comparisons where people would take one cell and say, oh, well, we've lost this amount of performance running it at a higher C rate. You've got to put that against the background of what range do we need these vehicles to do? I mean, there's already Teslas out there that have done 400,000 kilometers. So do we need vehicles to last that long? I mean, it's great if they do. I'm not sure that's the sort of I don't know, the society we're in. I own a car until I've driven it into the ground, but that's me. So I don't think other people do that. They're very recyclable. So if they do go through life quickly and degrade, I mean, so long as it's met a suitable life, which yes, these high power batteries can do, they can easily get over the 100,000 mile sort of level, way beyond that. And if they have the engineering put into them, which which has been lacking so far, that's definitely something that can improve further. So yeah, I think the smaller high power batteries can definitely go the distance, and then the recycling is taking off, and there's so much value in these batteries at the end of life, particularly if the raw material prices carry on going as they are, that they're going to get recycled and reused.
I think there's probably a future debate to be had there about the endurance of vehicles as well, isn't there? Talking about 400,000 kilometers Teslas, is it the car or the battery that fails first? But BMW's i3 design, particularly a high amount of carbon fiber content, you'd think it's sort of a chassis that's going to last a good number of years, and yet has been scuppered probably more by connectivity issues recently with 3G coming to a close. So they're losing connected drive functionality. Yeah. So it's not the batteries maybe that derives the life cycle of the car anymore.
Yeah.
Okay. So a question from Mehmet, which is, are there alternative materials that might replace lithium for the batteries that potentially offer, well, I guess a different balance, but lower cost is the question.
Sure. I mean, lower cost, if you're sort of like looking more towards like grid storage, there's definitely so sodium ion batteries work really well, are becoming available and should work really well for the really lower power, long energy, where mass doesn't matter too much. They're definitely coming along, and there seems to be quite a lot of development in that area. In the super fast charging side, there's companies like Nyobolt who are doing some great stuff in terms of super fast charging, but they're looking at sort of recharging in 2 minutes kind of ranges of stuff. So yeah, there's definitely work going on out there, but the lithium ion already sort of fills most of that middle range pretty well.
I think it's going to be interesting to see where maximum powers start to plateau compared to alternatives such as wireless charging within the roadway potentially offers something that keeps vehicles going without having to go to such high powers, I guess, arguably.
Yeah.
Right. Well, Paul asked, do you believe batteries will get smaller and follow the pattern that you've outlined today?
I think so. I think we'll still see a range. I think there'll be the customers who want to have that single charge range and who are prepared to pay the amount of money that is needed to have that size of battery. We see that there's a whole range of vehicles that are on the market today, from petrol vehicles, some of which you look at and you're like, how does that make sense? And they still sell. So there needs to be that range of vehicles. I think as we get to working out how we make these vehicles more cost competitive, available to a wider range of the public, it really needs to be about how much raw materials is going into them. How do we make the best use of those raw materials? And if we do get this supply issue, if the supply issues get worse, I mean, companies are going to have to decide, like, do they want to sell 2 top range vehicles, or do they want to sell 3 vehicles that are slightly lower spec? And how do they get the best value out of those lower spec vehicles? Well, actually, if they add fast charging into those vehicles, they can charge a premium on them. So I think there is some push on the OEMs to really think about the fast charging side of it and use that as a marketing tool to push the flexibility side of it. I think that's going forward is something that's going to keep their margins.
Yeah, you can definitely see it being a differentiating attribute, can't you, compared to range as it is today. Final question, potentially inflammatory here from Jonas. What about hydrogen as an alternative? That's a that's quite an open-ended question, I guess. We could answer that.
I don't know what the recharging kind of times are on hydrogen. It's not the same as filling your car with petrol, but I'm sure that the numbers right now, possibly towards the hydrogen stuff. I think on the flip side, like we don't have enough low carbon energy at the moment in my mind to be using hydrogen so widely for EVs. It loses so much energy in the conversion process, and we're not yet at 100% green grid.
It's about 2/3, isn't it, thereabouts?
Yeah, but not enough. And there's so many other things that hydrogen definitely does need to get used for. So I think all the green hydrogen that we can make, needs to go into aviation fuels, ammonia production, whatever it is that we're going to do about concrete. There's so many. It's a fantastic material. It definitely is part of the answer. I don't think it's necessary. I don't think it will actually win for EVs. I think the battery electric products are better already, and I don't see a driver for it.
I guess it's going to be interesting to see how it plays out, isn't it? In the market for commodities. Okay, that's the end of the questions from the audience. I guess one more question for you. Well, maybe a question for all of us. What do you think is the most significant EV on the market currently, and or why do you like it? Let's say.
Sure. For me, I think the Hyundai Ioniq 5, Kia EV6. I think I think at the moment they're the vehicle that is closest towards what I'm looking for from this. They've got a really good recharge time, and the battery packs aren't huge. They're knocking on the door of the recharge time of the Lucid Air with a battery that's I know it's not 50% smaller, but it's a decent chunk smaller.
Yeah.
Okay.
Cecile, what do you think? Do you have a favorite?
Yeah, I've learned a lot as usual preparing this episode. Thank you so much, David.
Do you have a favorite EV, Cecile? What's your favorite one?
No, I don't have favorite EV. What I like is to understand all the technology. I care about understanding how they work.
Excellent. I think I'll cheat slightly and look ahead into the future a little bit and say I think the Ioniq 6 I think will be very interesting. I'd like to see the Hyundai Kia brand returning to the efficiency and use metrics that you used to get out of the original Ioniq. I think it'd be nice to see that sedan body style and some lower consumption figures, but with all the tech as well, including being able to go camping, obviously, and charge everything off the car. Right. We shall bring it to a close, shall we? So thank you very much for your time, David, today and in the event. And thanks again to Cecile for walking us through that session.
And just want to mention to people, do not forget we have the 2 first episodes also available, so you can watch this online on YouTube.
That's right. Yes, we have all our episodes now on YouTube, where you can watch them to your heart's content, and you'll probably need to for some of the technical detail in some of these slides. So thanks for joining us, and we'll see you again soon. We'll be back in 2 weeks. We're expecting to be discussing in the same slot vehicle charging. And
thank you.
Thanks very much.
Bye, everyone. Bye, David.
Bye.
Cheers.